Ancient inflows carved their way into Osuga valleys, and the record of that passage survives in layered rock. Exposed outcrops stretch across a depression where sediments stacked up over time, each bed a chapter in a long and unfinished story. A previous observation caught only a fragment of this outcrop. Now, the wider view reveals far more. These layers appear to record inflow events directly tied to Osuga Valleys itself. Tracing their full extent helps constrain when water moved through here, why it stopped, and what ultimately shaped the enigmatic terminal depressions that define this ancient system. A massive impact once struck the southern highlands of Mars and punched deep into ancient crust. Rock from kilometers below the surface tore upward and then rebounded, forming a central pit that now preserves material no other process could ever reach. Colors shift dramatically across this pit, revealing a range of distinct rock types locked in place since before the present surface existed. Each exposure captures a different chapter of buried Martian history. Studying these uplifted rocks reveals how ancient Mars formed and how heat, pressure, and deep time quietly altered everything buried far beneath it. A crater floor near Noach's Terra holds bedrock that is unusually rich in olivine, a magnesium-iron silicate common in planetary mantles. On Mars, its presence signals something important. Olivine reacts with water and transforms into other minerals, so its survival here suggests limited aqueous alteration. While the broad shape of this crater is well studied, its fine-scale fractures and layering remain poorly understood. Mapping those structures could reveal large-scale crustal processes, including how Martian magmas formed and how regolith developed across billions of years of planetary history. Sedimentary layers in far eastern Candor Chasma do not stack randomly. They organize themselves into bundles of quasi-periodic beds, a rhythm that points to something far larger than local geology. This pattern may record orbital forcing, the influence of a planet's changing axial tilt and orbital path on its climate over time. Mars undergoes these planetary cycles just as Earth does. Testing whether orbital forcing drove sedimentation inside Valles Marineris would connect canyon rock directly to planetary-scale climate history, showing how deep time is encoded within layered Martian sediment. Olympia Undae holds some of the most distinctive dunes on Mars, built largely from gypsum swept across the northern polar region over time, where those dunes meet the flat-lying layers of the basal unit below them. A sharp boundary forms that carries real scientific weight. Gypsum-rich dunes and their underlying substrate may share a compositional history, or they may tell entirely different stories about how this landscape evolved. Examining this contact allows a detailed stratigraphic and mineralogical comparison between the two units, probing how the polar landscape built itself across deep Martian time. Branching ridges rise above the plains of the Eridania Basin, tracing patterns that once marked the floors of ancient valleys carved across this terrain. These dendritic forms may have connected to a larger channel system that erosion has long since erased. Sediments filled those valleys and slowly cemented into rock, stronger than anything surrounding them. Erosion then stripped away the softer terrain on all sides, leaving hardened valley fills standing above the surface. What was once low ground became elevated ground. The ridges now preserve the geometry of a drainage network Mars no longer runs. A small crater 1 kilometer across sits in the southern hemisphere of Mars, its slopes coated in frost that built up through the long Martian winter. South-facing walls stayed cold enough to trap ice as the planet tilted away from the sunday. That same crater, observed again as spring arrived, reveals a transformed landscape. Every trace of frost has vanished from those slopes, sublimated back into the thin Martian atmosphere. HiRISE repeat imaging makes this seasonal shift measurable, turning two snapshots taken months apart into a direct record of frost cycling across a single ancient impact bowl. West of Arabia Terra, layered strata reach through a landscape that holds the memory of deep Martian time. Adjacent images reveal isolated buttes with little stratigraphic overlap, leaving meaningful gaps in the geologic record. This region fills those gaps. Long sequences of layered rock stack here in near-continuous succession, potentially preserving the full paleostratigraphic column for this part of early Mars. Reading these layers from bottom to top reconstructs the ancient environment that produced them. building a timeline of changing conditions that shaped the planet long before the surface we see today came to exist. A canyon wall in Valles Marineris slices downward through billions of years of Martian crust, exposing layer after layer of volcanic or sedimentary rock. The Mars Orbiter camera imaged this same wall, but its resolution left the finer structure invisible. HiRISE reaches deeper into that detail, resolving individual boulders and structural features the earlier instrument could not detect. Enhanced color separates mineralogical differences within the strata. Stereo imaging measures the dip of each layer, turning a wall of rock into a three-dimensional record of how this canyon was built and later exposed. Fresh exposures burst through the reddish dust mantle along the north rim of Hale Crater, revealing blue, green, purple, and light-toned material at the sources of active channels. HiRISE near-infrared filters make these mineralogical differences visible where the eye alone would miss them. Gullies cut downslope from these exposures, but when they formed and what triggered them remains contested. Geologists read the timing of events through superposition relationships, determining which landforms buried which. Each layer of this crater rim is a clue in a puzzle that Martian geology has not yet finished assembling. 3 kilometers of dusty water ice pressed down on the North Pole of Mars, built from layers deposited over millions of years of climate cycling. Each band records a shift in dust content, ice purity, and atmospheric conditions stretching deep into Martian history. Erosion has carved scarps and troughs that slice open this archive. Tan layers dominate the upper stack, but below them, a section of bluish material appears, packed with sand-sized rock fragments that once formed a vast polar dune field. No ice cap covered the pole during that era. Mars was a different world, and those blue layers prove it. Dust devils spin across Mars every afternoon, drawing columns of fine material high into the thin atmosphere. Their dark tracks cross the surface like brushstrokes, and HiRISE records them across many regions. Capturing an active devil in the act requires timing. The camera covers small areas and arrives near 3 p.m. local time, just past peak heating when activity begins to fade. In 2008, an observation over the Amazonas region caught one in motion. Though the swirl extended beyond the color strip, these same twisters cleaned the solar panels of Opportunity and Spirit, quietly extending their working lives. A crescent dune inside Kaiser Crater carries the scars of every season Mars endures. Along its downwind slope, large gullies cut deep into the sand, carved each winter when frost drives dune material downslope and builds broad fan-shaped aprons at the base of every active channel. The upwind slope tells a completely different story. Dust devil tracks streak across the surface as dark lines and curlicues, left by spring wind vortices that systematically vacuum up thin dust layers and expose the darker dune sand beneath. 1 dune, 2 processes, 2 seasons, a surface that never stops reshaping itself. Wisla Cenis crater spans roughly 140 kilometers across Noachis Terra, and its slopes may hold one of Mars' most intriguing active features. Previous images suggest northwest and west, facing examples of recurring slope lineae, dark seasonal streaks that appear and fade on steep terrain. Additional observations confirm whether this site qualifies as a strong candidate. Beyond the lineae, light-toned rock exposed along the crater walls may carry hydrated minerals such as sulfates, pointing toward a possible ancient water environment buried within the geology of this enormous and eroded Martian basin. Eridania Basin sits at the head of Ma'adim Vallis, and mounting geomorphic and spectral evidence suggests it once held a vast ancient inland sea. Dark ridges cut across a brighter substrate in this HiRISE image, their origin still debated. They could be cemented and topographically inverted fractures, though eskers, channels, and volcanic dikes remain possible. Fluids moving through fractures would have hardened the material within. Erosion then removed the softer surrounding rock, leaving resistant cemented fills standing proud. This basin may have been long-lived and well-suited for ancient life. Gullies on Mars are not frozen in time. Repeat HiRISE imaging of this location reveals real and measurable change between observations. A lobate rubbly flow has been deposited near the mouth of the channel, and further up the slope, the channel system shows both erosion and fresh deposition. Changes have now been documented across many Martian gullies, and the pace is striking. The timing points consistently to winter and early spring, suggesting that carbon dioxide frost forming in and around these gullies each year is the force driving movement, carving and rebuilding these slopes season after season. Hebrus Vallis, carved through the northern lowlands of Mars, just west of the Elysium volcanic region. And this section reveals something unusual. Two impact craters, each roughly 200 meters across, sit within a channel system of remarkably uniform width, suggesting persistent flow rather than a single catastrophic flood. The geology reflects formation in volcanic terrain, where fluid erosion cuts into basalt interbedded with ash and sediment. The channel system dates to the early Amazonian, as far back as 3 billion years ago, making it younger than most outflow channels on Mars and shaped by a distinctly different set of ancient forces. At the highest latitudes of Mars, dry ice and water ice together sculpt a landscape unlike anywhere else in the solar system. Water ice frozen in the soil splits the ground into polygons, while dry ice sublimating in spring erodes and twists the channels between them. As a translucent dry ice layer develops vents, escaping gas carries fine surface particles outward, dropping them in dark fan-shaped deposits. Sometimes the dark material sinks back into the ice, leaving bright marks behind. Vents close and reopen as wind shifts direction, producing multiple fans from a single point, each aimed a different way. Inside an ancient and heavily eroded impact crater in Arabia Terra, a dark-toned mound rises from the floor, its surface punctured by irregular pits. The eroded crater rim signals extreme age. The mound within raises harder questions. HiRISE resolution reaches deep enough to probe textures that might explain it. Layering visible in pit walls could point to a sedimentary or ice-rich origin, while cracks from expansion suggest a different internal process. Whether sublimation carved these pits or something else formed them, this mound preserves evidence of processes that shaped Arabia Terra long before the present surface took form.